Hello, in this section we're going to talk about optimization problems. Now, one way of which that we look at optimization is that we always have an objective function that you're trying to either minimize or maximize. So for instance, if we happen to know that the perimeter of like a region happens to be 48 inches, so like if we have that the perimeter is 2x plus 2y, and then we have that the perimeter is equal to 48 inches, we can actually determine what is the largest possible area for this region. Not only that, but like what are the dimensions of it. So typically you'll be given something like this where you have to determine that this is the length, that's the width, and then you know that the area is length times the width. I already used x's and y's, so I might just need to use x and y. So knowing that, let's say that the equation, or knowing that 2x plus 2y is equal to 48, I know that y equals to 24 minus x. Now, if that's the case, then that means that the area is a function of x, meaning that we can use that the length times width, so that'll be x multiplied by 24 minus x. But in this case, this tells me that if I was trying to maximize the area, then in that case, I have that the domain is going to be from 0 to 24. Mostly because I need to have that this is always positive. So with that, let's just go ahead and say that we have area is equal to 24x minus x squared. Take the derivative if you want to maximize this. So that's going to be 24 minus 2x, but then you would set that to 0. So you would end up getting that 24 minus 2c equals to 0. And this gives you that c is equal to 12. Well, if that's the case, then basically you would just set up an interval line where you have from 0 to 24, but then you have 12. If you plug in values in between, like 1 and maybe like 20, you plug it back into the original. So this gives you positive if you plug in 1 into the derivative. And then you have that when you plug in 20, you get that that's less than 0 because 24 minus 40. Now what this means is that the function actually does increase towards 12. So that means that you have that there's a max. But more specifically, there's an absolute max. Okay, so we have that we can maximize the area if we let the length be equal to 12. So what that means is that you have that this is going to be a 12 inches by 12 inches for a maximum area of 144 squared inches. Now it is true that technically this becomes a square, okay, and that's just because of the nature of the values that we got. I mean, if we would have specified something different, maybe we would have got something else. Now, another typical question of which that you might have, for instance, is like if you have, let's say, like a sheet of material. If this sheet of material is, let's say, like 48 inches, and then you have 48 inches, but let's say that you want to cut some corners out of it. So, like, you cut a corner, you cut a corner, you cut another corner, and then you cut another corner or squares. If you cut like these little squares from here and you just label that as x, then what ends up happening is that you end up with that this right here is 48 minus 2x. And that would be the same on this side too. So if I was to remove these flaps or these corners and then fold it, I would basically just end up with something that looks like this. And then from here, I would just need to work it out. Now consider this. This rectangular box, it's basically kind of like it's got an open top. So here we would have to say that this is going to be x. This is going to be 48 minus 2x, and that's 48 minus 2x. Now, from here, you can actually just use that the volume, knowing that the volume is length times width times height, we can actually maximize the volume by saying that that's just going to be x multiplied by 48 minus 2x to the second power. Now, this tells me that basically the domain is from 0 to 24 because I need to make sure that it's strictly positive. Now, if I take the derivative, now actually let me just rewrite this. 4x times 24 minus x squared. Now, rather than using that we can FOIL this out, we can just say 4 times 24 minus x squared plus 4x times 2 times 24 minus x times negative 1. Now, notice that basically we have that this is going to be, let's factor out a 4 and let's factor out 24 minus x. So that's going to leave you with 24 minus x, and then that's going to be minus 2, minus 2x. So what this does is it gives us 4 times 24 minus x multiplied by 24 minus 3x. Now, notice that basically if we were to rewrite this, we would have 4 times 3 times 24 minus x multiplied by 8 minus x. Now, what that does is it tells us that we have a factors of 24 minus x and 12 and 8 minus x. Now, essentially, if we go ahead and we set up an interval line test, we can actually determine that which of these will give us, or what is 8, if it's the maximum or not. So essentially, this is the volume, and we're going to check to see, like, if you plug in 1, plug in 10, what's going to happen. So you plug in 1 into here, so v prime of 1 is equal to 12 times 24 minus 1 times 8 minus 1. But that's basically positive, so we know that that's going to be positive. And then if we plug in 10, well, you have that v prime of 10 is equal to 12 times 24 minus 10 multiplied by 8 minus 10. But that's less than 0. So I have that's going to be negative. What that does is that verifies that 8 is an absolute max. And furthermore, we can actually just go ahead and say that, well, if we want to find the okay, so yeah, basically it tells us that x is equal to 8 inches. That's the size of the square. But basically, like, what that's telling you is that you had 48 minus 2x. which basically that's just going to be 16. So that's going to be 32. So you have 32 inches. So what that tells you is that you're going to take 8 by 8, I'm sorry, 8 inches by 32 inches by 32 inches. Now, what that should give you is somewhere in the 8,000s. So 8 times 32 squared. That should give you a largest volume of 8,192 cubic inches. And then that's it. Okay, so that was actually not too bad. But one thing that you might run into is like questions that are a little more involved. Like for example, uh, let's say that you have like an offshore oil rig, and then let's say that you know that the shore is right here, but let's say that you have to get it over here, which this is going to be the oil company of which that you're trying to get it from here to here. Now, one thing that you could do is you could say, well, let's just model this using a right triangle. Actually, let me go ahead and use my trusty ruler. So, okay, so we just want to get from here to here. It's a little off, but that's okay. Um, okay, so if we label this as x, and let's say that we know, for example, that this right here is like 18 miles. Well, it would be more or less likely to be more expensive if we construct an oil pipeline um, directly underwater. Mostly because, like, yeah, sometimes it's like more expensive to try to construct it completely underwater. Now, in this case, like, we would have to basically just say, well, what if we can actually just construct it somewhat underwater, but maybe like to another point? So, like, say for example that we were to construct it in a way that it would actually be better if we can construct it. Maybe, let's see, let's pick a point, like pick a point right here. So if we pick a point right there and we kind of construct it like this, and then we just build the pipeline along shore, well, what this does is it tells me that essentially I have that the distance that I have for this right here, this is going to be, okay, so let's go ahead and just rewrite this a little bit. So suppose that, that this oil rig is, let's say, 8 miles offshore. Okay, so we can actually label this as x and this as 18 minus x. So that way we just need to find this line and this line. So that would mean that that would be the cost is equal to, okay, so maybe like the cost of whatever it is for underwater drills multiplied by the distance, which in this case would be x squared plus 8 squared. plus the cost that it would be for onshore pipeline. So that would be this times 18 minus x. This is a typical problem that you can use for optimization or applications of extremas. So, like whether the cost of the underwater pipeline was like 10 million and this is going to be like 5 million, you're going to still plug it into here because this gives you the cost of the pipeline. Definitely, if you do a direct pipeline, it's going to be more expensive. If you do kind of like a, taxi cab, like down and to the right, it's still going to be a little bit expensive. But if you kind of like find a midway point, not midway, but just like a combination of underwater and onshore, then that's going to work out nicely. But the interesting part of this is like, what value is that tells you where you should start drilling onshore? Not drilling, but start building the pipeline where the underwater meets with the onshore. And it's actually pretty nice, the solution. Like if we have the respective costs for C1. So I'll have to put somewhere here that C1 is cost of underwater pipeline, and that C2 is the cost of onshore pipeline. So if you figure out that X is like 1.1, then that'll tell you, what's the distance for here and like what's the distance for here. Ideally, it's mostly the case that the underwater pipeline is the one that costs the most. So in that case, you want to try to shorten this as much as possible, which means that this will be really close to wherever this meets right here.